Steinhauer here, welcome back. We have taken a high mass star from the main sequence and gotten it to the stage where it is has an iron core, an inert iron core, and it's burning in successive shells elements like silicon and oxygen and carbon and helium and hydrogen. So you've got this iron core, and it is supported by electron degeneracy. and it turns out there's a fundamental limit for how big a thing you can make that is supported by this electron degeneracy. Remember, electron degeneracy is that fact of quantum mechanics where two fermions, in this case electrons, can't occupy the same quantum state. They can't be in the same position at the same time with the same energy. And that provides a limit of how massive a thing you can make with this. And that limit's about 1.4 times the mass of the sun. Once you make an object that's more massive than 1.4 solar masses, and that will happen, right? As soon as you start making this inert iron core, there's nothing to stop it from growing. As soon as you run out of silicon in the region, you have an inert iron core, and this thing will just get more and more and more massive as more and more iron gets dumped onto it. Once you surpass the Chandrasekhar mass limit, the core can no longer support itself. And it must collapse. So something has to happen to all of those iron atoms, and something has to happen to all those electrons, because again, you can't squeeze anything more closely together that has a bunch of electrons in it. So they have to go somewhere, and they have to go somewhere fairly fast and fairly suddenly. So what actually happens? The iron atoms are actually completely smashed apart. The photons that are running around in this soup now that is several billion Kelvin hot are so energetic that they can undo all of the work that was done to create them in the first place, right? And so in a process called photodisintegration, which is one of the best words of all time, let me write it down. Photodisintegration, you know what disintegration means, to tear things apart. Photo means light. So this means to disintegrate, to tear things apart by light itself. And that's exactly what happens. These iron atoms absorb photons that are so energetic that they can rip the iron atoms apart and turn them back into protons and helium nuclei. So that is an energy sink now in the center. Normally you've had an energy source in the center of your star that's been supporting you. All of a sudden, all these iron atoms are absorbing energy instead of creating energy. And that's a big problem for your star. Now the electrons have to go somewhere too, because in order for this thing to collapse in on itself, those electrons have to go away. What physically happens to those electrons? They actually will combine with protons, P plus E minus. This is a proton plus an electron, and that they will combine together to make a neutron and a neutrino. That's the Greek letter nu for neutrino. So you've got a lot of protons. All of these iron atoms have been photodisintegrated down into their protons. Those protons will combine with electrons to make neutrons and neutrinos, and basically all of the electrons will be turned into neutrons and neutrinos. And so you no longer have a source of energy at the center of your star. You no longer have a thing that supports your star either. And the entire 1.4 solar mass core collapses in on itself. It no longer has any way to support itself. So a very short amount of time later, less than a second, this thing takes to go from something about the size of the Earth down to something that is much, much smaller than that. And at that point, depending on how massive the star is, neutron degeneracy will kick in. So remember, electron degeneracy was what was supporting white dwarfs and what was supporting the star, the core of the star, before it collapsed. Those electrons went away, but neutrons are also fermions, and they also behave this rule where you can't get any two neutrons in the same place at the same time, in the same quantum state, and the same energy level. only you can get neutrons a lot closer together than you can make electrons. But there's still a limit. When you reach that limit, assuming that there aren't too many neutrons, assuming you're not too massive, then neutron degeneracy will suddenly stop it at the bottom. And that sudden stop at the bottom causes a bounce. And it's an extremely energetic bounce. And it's a bounce that sends shock waves rippling through the outer part of the star and ultimately blows the entire star apart. So this is a catastrophic failure of the star. The outgoing bounce material slams into the material that was falling in on it because the whole thing was collapsing just a short time ago. And the outgoing material has more energy than the ingoing material, and the outgoing material wins, and the entire star explodes from the inside out. Now, this is not just a spherically symmetric thing necessarily. I've shown some diagrams here from actual simulations of this process that show you how turbulent and chaotic it is when outgoing material slams into ingoing material. This is the entire star then, outside of the central core, which is now composed of neutrons, will explode from the inside out. So what do we call such a thing when we have a star exploding from the inside out? We call it a supernova. Why do we call it a supernova? Well, nova, the root word nova means new star. And there are things that are called novae. These things are bright white dwarfs, basically, that have surface hydrogen fusion going on for short periods of time, and you'll get what is normally a very faint star all of a sudden getting very bright for a few weeks. And this, of course, freaked the ancient people out because they thought the heavens were immutable and perfect, and when new things pop up into it, it was usually a bad thing. And so new star makes sense, right? And so supernova is also a new star, except these things are much more energetic than classical novae are. And so for a supernova, the luminosity of a star, which was already one of the most massive and luminous stars in the galaxy, increases by a factor of millions, tens of millions, maybe hundreds of millions. And it can briefly outshine the entire galaxy in which it is located. Here is an example of a galaxy and an example of a supernova that went off in that galaxy. And you can see the brightness of this one star as it's exploding is brighter than the combined light of the entire galaxy, the rest of the galaxy in which it is housed. And so these things, supernova is a pretty good word for these things. They are among the brightest things, the most luminous events that happen in the universe. Okay, and they're really important for the universe, right? This is how much of the stuff that we take for granted in our everyday lives gets made in the universe, right? Remember, the early universe, when the universe first began, was basically just hydrogen and helium with trace amounts of other light elements like lithium and boron. But that's almost not even enough to even talk about. Every single other element that we have in our everyday lives was formed in stars somehow. And these supernovae make pretty much everything that is more massive than iron. All the gold and all of the silver and all the uranium and all of everything that's heavier than iron on the periodic table pretty much was made in these events, right? You've got huge densities, you've got huge temperatures, you've got neutrons slamming into other protons and other elements and fusing with them to make heavier elements. And you don't need to make energy because you've got huge amounts of energy because these things are slamming into each other at enormous speeds. And so all of these elements can not only get made in these events, they get blown out into space by these extremely powerful explosions. And so the next round of stars that are formed will have these elements in it. And the more of these that go off, the more of those elements are in the universe, and the more that can be used to form a planet like Earth that has all of these elements synthesized into it. So these supernovae are important for lots of reasons, but one of them is it is the main source of all of the elements beyond iron in the universe. Okay, they're also very cool objects. Remnants of supernovae can glow for thousands of years. These things are very, very energetic events. They can be bright in X-rays. Here's an example of a supernova remnant Cassiopeia A in X-rays on the left and in radio waves on the right. Again, it's the same remnant. You're just seeing different aspects of it in these very high energy photons and very low energy photons. And this one looks fairly spherically symmetric, but not all of them do. There are some other pretty pictures of supernova remnants, and you can see they have very different morphologies and colors, although that's usually just a false color thing, and shapes. And these are, depending on how old the supernova remnant is and what wavelengths of light we're imaging in it, these things can look very different, but they can glow for thousands of years. They are that energetic. Okay, there is a particular supernova that I want to talk about, which went off, which is called supernova 1987A. It is the first supernova that went off in the year 1987, which is why it's called 1987A. We're not that creative at naming things in astronomy. And this is important because it is the closest supernova to have gone off in the modern era. And it wasn't even in the Milky Way galaxy. It was in a galaxy that was that is a satellite to the Milky Way galaxy, the Large Magellanic Cloud. And this is an interesting story too, actually. The last supernova that we know of that went off in the Milky Way galaxy was observed by Tycho Brahe in the 1600s, which has been a long time. When we look at other galaxies, we see on average that most galaxies have a supernova go off about once per century. So we're way overdue for a supernova to go off in this galaxy. And if it does, it'll be pretty spectacular because we can probably, if it's nearby enough, we can see it with the unaided eye. And that's just a pretty cool thing. Anyway, supernova 1987A was almost that. It was visible with the naked eye easily. It became one of the brighter objects in the southern sky, although it's not visible wasn't visible from Geneseo. It became one of the brighter objects in the southern sky from southern hemisphere observatories. And it is still the only one, I think, that has gone off whose progenitor is known, meaning we had measured and studied the star that went supernova before it actually went supernova. Most of the time, these things are happening in galaxies that are so far away, we haven't actually characterized the star before it goes supernova. This one we had given it a luminosity class and a spectral class. It was a B3 supergiant, B3 being the spectral class and one supergiant being the luminosity class, which is good. We expect supergiants to go supernova, right? It would have been surprising if this were a K5 star, right, on the main sequence. We don't expect those stars to go supernova. So that's, it's nice when your theory matches up with what you actually see in real life. Okay, so this thing, here it is. Some pictures of this thing. You've got this is the star before it went supernova, and this is the star after it went supernova. I'm not sure why we got this number wrong here, but this is the object itself became one of the brightest objects in the sky after it went supernova for a matter of a few weeks until it faded off and was no longer that bright. What does it look like today? This is fascinating. This is what that object looks like in more recent times, right? What the heck is going on here? Why does it look like this? You've got 3 rings, and a dot in the middle. So the dot in the middle is probably where the supernova went off itself. You've got a ring around it there, and then you've got 2 other fainter rings that don't even seem to be centered on the original ring, there and there. What the heck is going on here? This is actually a very cool thing. So this is where I want you to remember back to the last video where we looked at Eta Carina and saw how it had, before it went supernova, because it hasn't gone supernova, had emitted lots of materials in 2 lobes that kind of looked like an hourglass. We think that this star probably did that same thing. So here's a diagram again on the right. On the left, you see the thing. And on the right, you see a diagram of what we think is going on. So again, we think that this star had two lobes on either side that were a material ejected while this star was just a massive star living its life. And then when the supernova went off, the shock wave propagates through that material. And that material has been nozzled in such a way that the shock waves appears as these rings as it passes through the previously ejected material and causes it to light up and heat up and glow for a short time as the supernova shock wave expands along it. And so that is, again, very cool way to study not only the supernova itself, but the material around a very massive star as the shock wave propagates through it. You can learn a lot about high mass stars and about the process of supernovae and lots of other things by studying the rings and how they change. And here is an example of how the rings changed from over the course of about 15 years from 1994 to 2009. And you can see all kinds of cool brightenings and darkenings and shape changes and interesting things have gone on with this object since. Okay, we will come back in the next class and talk more about the remnants that are left behind when stars die. So hope to see you there.